So picture this. It's a bustling corporate enterprise, right? Monday morning.
Oh, the absolute busiest time of the week.
Exactly. I mean, the coffee is brewing, the European markets are already mid-session, and the executive teams at headquarters are just logging on.
The operations are just humming along perfectly.
Right, humming along, and then completely without any warning, the entire enterprise just grinds to a catastrophic halt.
Wow.
Yeah, we're talking 40% of the company's internal endpoints just suddenly compromised. Customer databases are totally locked down.
A total nightmare for any IT director.
A complete nightmare. Global supply chains freeze in their tracks. Down in the Security Operations Center, the incident response team is just staring at a wall of red alerts. They are completely paralyzed.
I can literally feel the panic from here.
Right. Now, when the postmortem's finally conducted, weeks later, the board of directors fully expects to hear about some highly sophisticated nation-state attack.
Or like a compromised executive password used by a massive ransomware syndicate.
Exactly. Something out of a spy movie. But the actual culprit.
Let me guess. It was something incredibly simple.
It was a single, unauthorized, completely unpatched Internet of Things device. A smart thermostat, to be exact.
Oh man, a thermostat. It's always the smart devices.
Always. It was plugged into this overlooked, dusty Ethernet port in a remote edge network location like maybe your regional distribution warehouse.
Just sitting there in a closet somewhere?
Yep. And from that single physical port, the malware completely bypassed the multi-million-dollar corporate firewall sitting at the perimeter.
Because it was already inside the house, essentially.
Exactly. It traversed the internal networks and literally brought a Fortune 500 company to its knees.
That is just, it's a scenario that keeps chief information security officers awake at night.
Absolutely. So as an enterprise executive or, an IT leader listening to this, how do you prevent this specific, terrifying vulnerability?
Right, because you can't just buy a shiny new firewall and call it a day.
You really can't. You prevent it by mastering the underlying physical and logical infrastructure of your data communications.
Which is exactly what we are going to unpack today.
Yeah.
Because the terrifying reality is variations of this happen every single day.
Every day.
Organizations just pour massive capital into perimeter defenses. It's like the digital equivalent of building a massive moat and a steel drawbridge.
A giant fortress.
Right. But if you don't fundamentally understand the physical wires, the foundational network services, and the incredibly granular access controls operating inside your own walls.
You're flying totally blind.
Completely blind.
Yeah.
I mean, a fortress is totally useless if you just leave the back door propped open for a thermostat.
Well said. And that structural blindness is exactly what we are dismantling today. We're going to pull the network apart down to the bare copper wiring.
And then build it all back up into a secure, monitored, enterprise-grade architecture.
That's the plan. But before we cross that threshold, I want to formally invite you to like, subscribe, and share this deep dive. You really want to do this so you always maintain a competitive edge in the hyper-connected marketplace. Technology just moves ruthlessly fast, right?
Oh, incredibly fast.
And our goal is to keep you at the absolute bleeding edge of strategic management. Also, you will definitely want to check the description below for access to additional corporate resources, architectural diagrams, and the technical reading that supports today's analysis.
Because, frankly, building a resilient infrastructure isn't just some low-level IT mandate anymore. It is the absolute core foundation of modern business continuity.
Absolutely. You cannot run a business without it. Now, for those of you tracking with our overarching graduate-level series, this is Chapter 9, Network Infrastructure Implementations.
Out of our comprehensive 15-chapter deep dive into telecommunications for managers.
Right. So to set our bearings, let's briefly look back at Chapter 8. In that discussion, we explored how Layer 3 routing metrics, link state protocols like OSPF, and distance vector protocols like BGP govern the logical flow of data across vast internetworks.
We examined how dynamic routing ensures resiliency, right?
Yeah, exactly.
Yeah.
Automatically calculating new paths to keep packets moving, even when a primary fiber line gets completely severed halfway across the country by a backhoe.
The infamous backhoe fade.
Always the backhoe.
But, Layer 3 gave us the logical map. It showed us the mathematical algorithms that routers use to make decisions. But routing protocols are software.
They're conceptual.
Exactly. They are entirely conceptual. Today, we have a very, very different mission.
Today, we step out of that logical map and onto the physical terrain. We're transitioning into the physical and hosted realities of the network.
Getting our hands dirty, so to speak.
Exactly. We are going to examine the automated services, the advanced hardware devices, and those rigorous access controls that allow corporate managers to actually see, manage, and secure every single asset on their network.
We are moving from the abstract algorithms to the concrete blueprint of the enterprise.
And that blueprint is where strategic investments are actually made.
Oh, 100%. And to understand how an enterprise network is physically constructed, we have to break the network hierarchy down into its three primary architectural components.
For sure.
The edge network, the distribution network, and the core, which is often referred to as the backbone network.
Okay, so I always find it really helpful to visualize this physical infrastructure kind of like the road system of a major metropolitan city.
Love that analogy. Let's run with it.
Okay, so let's start at the edge network. In our city analogy, the edge is basically the driveways, the parking lots, the little cul-de-sacs.
Right, the access layer.
Exactly.
Yeah.
It's where your endpoint connections live. You know, the employee laptops, the network printers, the VoIP phones sitting on the desk.
The barcode scanners in the warehouse.
Yep, and yes, those inherently risky IoT smart thermostats. The edge is where the human user, or the physical device, directly interfaces with the corporate network.
But just like a driveway, right? The traffic generated at the edge has to actually go somewhere to be useful.
You can't just sit in the driveway.
Exactly. And that brings us to the distribution network, which functions essentially like the local surface streets, the traffic lights, the highway on-ramps.
It's pulling everything together.
Right. Its primary job is aggregation. It takes hundreds or even thousands of those individual endpoint connections from the edge switches, and it funnels them toward the main highway.
Applying some routing policies and filtering along the way, I imagine.
Exactly. It's the traffic cop.
Which ultimately leads us to the core, or the backbone network.
The big one.
Right. This is the multi-lane interstate highway of your enterprise. It's the primary ultra-high-speed aggregation point that ties literally everything together.
Your local area networks, your wide area networks, your central data centers, they all connect here.
And it doesn't care about endpoint policies or filtering, right? Like, it just wants to move fast.
Exactly. It is designed for one singular purpose, moving massive amounts of data as fast as physically possible.
So what's the strategic implication here? If I'm an IT executive managing a massive budget, why do I care about this three-tier architecture?
Because you have to recognize where your critical fault domains lie.
Fault domains, meaning where things can break.
Exactly. The core network is a massive central choke point. Hardware performance and redundancy here matter more than anywhere else in the entire enterprise.
Let me put that into a business context for a second. If a 24-port switch fails at the edge network, say down in the marketing department.
Right, a localized failure.
Yeah, maybe a dozen employees lose their intranet access for an hour while a technician swaps out the hardware. It's an annoyance, sure.
But it's not a disaster.
Right. But if the core backbone router fails, and you haven't engineered any hardware redundancy,
the entire global enterprise goes dark, the e-commerce site drops, the warehouses halt, the VIP system completely dies.
the blast radius is just massive.
Exactly. The blast radius of a failure dictates your level of capital investment.
That makes total sense.
But
I have to challenge the traditional view here for a minute.
okay, bring it on.
So we are talking about physical cables and driveways. But if a company is moving toward a permanent hybrid work model, which, let's be honest, is the reality for almost every major enterprise today.
Absolutely. The landscape has changed.
Right. How does that change where they invest in this quote-unquote road system? If 60% of my workforce isn't actually sitting in the corporate office plugging into a wall, does that physical edge network still demand the same massive level of investment?
That, right there, is the defining architectural question of the modern era.
It has to be, right?
Yeah, it completely redefines our whole concept of the network perimeter. When you have a massive remote workforce sitting in coffee shops and home offices, you cannot just let them tunnel a VPN directly onto your corporate interstate highway.
Right, because their home network is probably full of infected thermostats, too.
Exactly. That is a massive security risk. So instead, you have to route them through a DMZ, or a demilitarized zone.
Okay, so I hear DMZ thrown around a lot in security meetings. How does that actually function mechanically in a modern network?
So a DMZ is a dedicated subnetwork, often implemented as a virtual LAN, or a VLAN, and it acts as a secure, heavily monitored buffer zone.
A buffer between what and what?
It sits right between the untrusted public internet and your highly trusted internal core network. The DMZ uses public-facing IP addresses, and it hosts the services that external users actually need to interact with.
So like your web servers, your email server.
Your VPN concentrators, exactly.
Okay, so it's basically like an embassy in a foreign country.
Oh, that's a good way to look at it.
Yeah, it's a controlled entry point where external entities can conduct their business without being allowed full, unrestricted access to the actual capital city.
That is a perfect analogy. Remote workers hit the DMZ, they are authenticated, their traffic is heavily inspected, and only then are they granted highly specific, limited access to the internal resources they actually need.
Not a free pass to the whole network.
And never a free pass.
So understanding this physical hierarchy, the edge, the distribution, the core, and the DMZ, it's really about understanding how traffic flows.
Yeah.
But all that traffic is ultimately trying to reach the data. And that leads us to the physical reality of where the data actually lives.
Wow.
The hosting infrastructure.
Right, the destination.
Exactly. And our source material outlines 4 primary paradigms here: the server room, the data center, colocation hosting, and cloud hosting.
And the distinction between these 4 isn't just some technical trivia. It actually represents a massive shift in corporate finance and risk management.
Okay, let's break that down. Let's start with the most basic one, the server room.
This is exactly what it sounds like. It's a small room or maybe a fortified wiring closet within your office building.
Nothing too fancy.
Right. It holds a few racks of servers, basic cooling, some physical access controls. It is entirely managed by local IT.
But obviously, once a company scales beyond a certain point, a repurposed closet with an extra air conditioner simply won't cut it.
No, things get too hot too fast. You have to move to a data center.
Right. And an enterprise data center is a massive, dedicated facility built specifically to support large-scale computer systems.
We are talking raised floors for cabling, specialized HVAC systems for the thermodynamics, redundant power grids.
Diesel backup generators,
Yeah.
enterprise-grade physical security,
Yeah.
like biometrics, man-traps, 247 armed guards.
Serious infrastructure. But here is the problem. The capital expenditure, the Capex required to actually build, power, and secure a private data center is just astronomical.
Most businesses are not in the business of real estate and thermodynamics.
Exactly. They want to sell shoes or logistics software, not manage diesel generators, which is precisely why we've seen this massive industry migration toward colocation and cloud hosting.
Because they solve that massive CapEx problem.
They solve it in different ways. In colocation hosting, or colo as it's called, a provider builds the massive, secure, power-redundant data center facility.
Okay, so they own the building.
Right. And you, as the enterprise, lease a physical cage or just rack space inside that facility.
Ah, okay.
The key differentiator here is that you still buy, install, and run your own physical IT equipment.
So I still own the servers and the hard drives.
Yes, you are just renting the premium environment to house them securely.
Got it.
Yeah.
So colocation gives you the security and power redundancy of a massive data center, but you still maintain absolute physical control over your actual hardware.
Exactly. Which I imagine is highly critical for regulated industries, right?
Oh, absolutely. Finance, healthcare, they love colo because they can physically point to the server and say, that's ours, nobody else touches it.
Right. But then we have cloud hosting, which takes that abstraction one step further.
How so?
In cloud hosting, you lease the entire infrastructure. You lease the virtual servers, the operating systems, the storage space. You do not own a single piece of physical hardware.
Nothing at all.
Nothing. The cloud provider owns the servers, the racks, the building, the cooling, everything.
So from a business perspective, switching from an on-premise data center to a cloud hosting model completely transforms the financial structure of the IT department.
It's a night and day difference.
You move away from Capex, having to buy millions of dollars of depreciating hardware every 5 years, and you move entirely to Opex, or operational expenditures.
Yes. You just pay a monthly utility bill based purely on the computing power you consume, just like a water or electric bill.
That's incredibly appealing to a CFO.
Oh, they love it. But while the financial flexibility is incredible, if we look at the strategic implications, it also fundamentally alters your security perimeter.
Okay, let's contextualize this. Give me a real-world enterprise architecture example.
All right, imagine a massive global logistics company. They operate a multi-site wide area network, and they utilize MPLS.
Multi-protocol label switching.
Right. Now, MPLS is an incredible technology because, unlike traditional routing that has to stop and look up an IP address at every single router hop.
Which takes time.
Exactly. MPLS just attaches a short label to the packet right at the edge of the network. The core routers just read that label and forward it instantly.
It's acting more like a high-speed rail switch than a complex four-way intersection.
That's a great way to put it. It vastly speeds up the transit time across the core network.
So how does this tie into cloud hosting?
Well, this logistics company uses MPLS to securely connect a massive regional distribution warehouse directly to a cloud-hosted inventory database.
Okay, so the data is in the cloud, but the warehouse is physical.
Right. So when a frontline employee scans a pallet on the loading dock, that data packet enters a wireless access point at the edge network,
Travels across the warehouse's local distribution switches.
hits the edge router, and then enters the MTLS WAN. It shoots across the country over the provider's core backbone, exits into the cloud hosting provider's infrastructure, and writes the data to a virtual server.
And all of that happens in a fraction of a second.
Literally milliseconds.
It's an incredible symphony of physical hardware.
It really is.
But here's the stark reality, and this is something I really want to emphasize. Building that physical road system, laying the fiber optic cables, racking the servers, configuring the MPLS links, is really only step one.
Right, it's just the plumbing.
Exactly. If you just plug all this expensive hardware together, nothing will actually happen.
Yeah.
The network is completely dark.
Just a bunch of blinking lights.
Right. To make the infrastructure actually functional, managers have to layer on automated foundational network services. Without these services, it's just a pile of very expensive disconnected silicon.
I completely agree. The physical layer is totally useless without the logical services that govern how traffic is identified, addressed, and directed.
They operate quietly in the background.
They do. They really are the unsung heroes of the enterprise network. And we need to dissect 4 critical protocols today, starting with IPM.
IP address management.
Right.
So IPM is essentially the methodology and the software used for planning, tracking, and managing the entire IP address space across a massive corporate network.
Yes. And according to our sources, you don't just hand out IP addresses randomly.
Doing so would create absolute administrative chaos, right?
Total chaos. Best practices in IPAM dictate carving up your network into highly structured subnets and then reserving specific IP address ranges for specific classes of devices.
Let's illustrate that for the listeners. Say we have a block of addresses. A network architect might reserve IPs ending in 1 through 100, strictly for employee workstations and laptops.
Okay.
And then IPs 101 through 150 might be reserved exclusively for network infrastructure, like your routers, switches, and wireless controllers.
Makes sense.
Then maybe 151 through 200 are carved out for internal databases and application servers.
And 201 through 250 are dedicated to those public-facing hosts sitting in that DMZ we talked about earlier.
Exactly. Now, a casual observer might think IPAM is just, obsessive administrative bookkeeping.
Right, just a spreadsheet for the IT nerds.
Yeah, but the reality is that IPAM is actually one of your most vital cybersecurity and incident response tools.
Absolutely.
But how does organizing numbers on a spreadsheet translate to active cybersecurity?
Well, think about it from the perspective of an analyst sitting in the Security Operations Center. Let's say it's 2:00 a.m.
Always 2.0 a.m.
Always. Suddenly, the intrusion detection system flares up. It's flagging massive amounts of encrypted outbound traffic trying to leave the network, originating from the IP address 192.168.175.
Okay, so if the network is just a random free-for-all, the analyst has to scramble.
Right. They have to cross-reference MSE addresses, log into switches manually, and try to figure out what physical device that IP even belongs to.
Is it a guest on the Wi-Fi watching Netflix, or is it something serious?
Exactly. But if they use strict IPM blocks, if the enterprise enforces strict IPM, the analyst sees the .175 address and instantly knows, without looking anything up, that this address falls in the block reserved strictly for internal servers.
Wow.
They instantly know that a critical piece of infrastructure is actively exfiltrating data.
That immediate, unquestionable context completely changes the incident response protocol. It goes from a low-level ticket investigation to a full-scale, code-red emergency response.
Instantly.
Yeah.
That structural context saves minutes.
And when dealing with a ransomware deployment or data exfiltration, minutes are measured in millions of dollars of liability.
Tens of millions, easily.
But this raises a mechanical question for me. I know that in an enterprise with, say, 40,000 employees, there is not a team of IT interns walking around manually typing IP addresses into every single laptop and smartphone.
God, no. That would be impossible.
So how are these addresses actually distributed?
That automation is handled by DHCP, the Dynamic Host Configuration Protocol.
Okay.
DHCP is the service that automatically allocates IP addresses, subnet masks, and routing information to endpoints the exact millisecond they connect to the network.
The mechanism behind this is fascinating. Our sources refer to it as the DHCP discovery process or the Dora process.
The Dora process, yeah.
Can we walk through the actual mechanics of how a laptop negotiates its identity on a network?
Sure. So Dora stands for Discover, Offer, Request, and Acknowledge. It's a 4-step process.
Okay, step 1, discover.
Right. When you walk into the office and open your laptop, it has no idea where it is. So it sends out a DHCP Discover message.
But it doesn't have an IP address yet.
Exactly. Because it doesn't have an IP address to send a targeted message, it sends a broadcast Ethernet frame to every single device on the local network segment.
It's essentially standing in a crowded room and shouting, I am new here. Is there a DHCP server that can give me an address?
That is literally what it's doing. The laptop just shouts into the void.
Shouting into the void. Okay, step 2, offer.
Yes. The DHCP server hears that broadcast. The server checks its IPAM pool to see what addresses are available and replies directly to the laptop's ME address with a DHCP offer.
Like, I can offer you the address 192.168.1.55.
Precisely. But the laptop doesn't just take it immediately.
Why not?
Because there might be multiple DHCP servers on a large network for redundancy. It wants to make sure it's formally accepting one specific offer.
Okay, which brings us to step 3, request.
Right. The laptop formally sends a request message broadcasting to the network, I am accepting the offer of 192.168.1.55 from this specific server.
And finally, step 4, acknowledge.
The server sends an acknowledge packet essentially saying, confirmed, the address is yours.
It's an incredibly elegant 4-step dance, and it happens in milliseconds.
You don't even notice it when you open your laptop.
But the crucial caveat here, and this is important, the laptop doesn't own that IP address forever. It's not a permanent deed to the property.
No, not at all. DHCP hands out addresses on a lease. A DHCP lease might be configured for 8 hours or 24 hours or a week.
And when it expires?
Well, when a certain percentage of that lease time expires, the laptop quietly contacts the server and asks to renew it. If the laptop is still connected, the lease is extended.
I've always thought of it kind of like hotel room keys.
Oh, that's a good comparison.
Yeah, like when you check in, the front desk gives you a key card that grants you access to room 405, but you only have access for the duration of your stay.
Right.
When you check out or your reservation time expires, that key stops working, and the hotel puts room 405 back into the pool to be handed to the next guest.
Exactly. If an employee takes their laptop home for the weekend, their lease expires, the IP is returned to the pool, and the network doesn't run out of addresses.
It is a brilliantly efficient system. So IPAM organizes the addresses and DHCP distributes them. But we still have a fundamental human problem.
We humans are terrible at remembering long strings of numbers.
We really are. If you want to access the corporate payroll server, you don't want to type 10.45.192.12 into your browser.
No, which is why we rely on DNS, the domain name system.
Yeah, I know the cliche analogy for DNS is that it's the internet's phone book.
I hate that analogy.
I know, it always felt a bit simplistic for an enterprise discussion.
It is overly simplistic. A much better way to conceptualize DNS in a modern enterprise is to view it as a massive, decentralized, real-time logistics routing matrix.
Okay, expand on that.
DNS is the protocol that translates human-readable domain names like payroll.corporate.com or www.amazon.com into the machine-readable IP addresses that the network routers require to actually forward the packets.
And it does this through a recursive lookup process, right? It's not just one giant database sitting in a basement somewhere.
Exactly. If your local DNS server doesn't know the IP address for a specific domain, it queries the global root servers.
Which direct it to the top-level domain servers.
Right, like a .com or .org servers, which then direct it to the specific authoritative server for that organization.
It is a highly distributed, tiered architecture that resolves billions of queries a second globally.
It's wild when you really think about it.
So we have organization, distribution, and translation. But our sources highlight a fourth foundational service, and honestly, this might be the most critically overlooked protocol in the entire IT ecosystem.
You're talking about NTP.
NTP, the Network Time Protocol.
NTP is the protocol used to synchronize the system clocks across every single computer, server, router, switch, and firewall in the enterprise.
And it usually ties back to standard, highly accurate atomic clocks run by organizations like NIST, right?
Yes, the National Institute of Standards and Technology.
Now, I've sat in meetings where executives actively scoff at time synchronization projects. The sentiment is usually, who cares if the firewall thinks it's 2:04 p.m. and the database server thinks it's 2:05 p.m.? The work still gets done.
That is such a dangerous mindset.
It is, because if we extrapolate the legal and forensic implications of just a 1-minute drift, the reality is terrifying.
A 1-minute drift is a massive corporate liability. Let's look at a post-breach scenario.
Okay.
Your enterprise has suffered a massive data exfiltration event. The very first thing your internal digital forensics team, external incident response contractors, and federal law enforcement are going to ask for are your system logs.
Because they need to build a timeline. They need to know the exact sequence of events to understand how the attackers moved laterally through the network.
Precisely. They need to know, did the firewall successfully block the malicious command and control packet before or after the internal database server initiated the massive data export?
Oh, I see. If your system clocks are drifting, if your edge router is off by 12 seconds, your firewall is off by 2 minutes, and your core switch is off by 40 seconds.
Those logs are fundamentally useless.
Wow.
They are completely inadmissible in court. You cannot prove a definitive timeline. You cannot piece together the attack vector because the sequence of events is entirely scrambled.
So you will fail regulatory compliance audits, you will face massive fines under frameworks like GDPR or HIPAA, and you will be completely blind during a forensic investigation.
All because you didn't sync the clocks.
Which gives us a very clear, highly actionable takeaway for managers listening. You must mandate verified, redundant NTP synchronization across every single piece of infrastructure you own.
It is not an optional configuration setting. It is a foundational requirement for legal compliance and rapid incident response.
Absolutely. So understanding how traffic is named, addressed, and timed leads us naturally into the physical reality of the hardware.
We need to understand the specific devices that actually process this traffic.
And strategically, where they belong in the architecture. Let's talk about hardware placement.
We can start with the basic building blocks, the devices most people are familiar with, LAN switches.
LAN switches.
Right. These are the foundational Layer 2 devices used for departmental workgroups. They operate down at the edge layer, providing the physical Ethernet ports for endpoints to connect.
Okay, and then routers.
Routers operate at Layer 3. They are heavier duty, highly intelligent devices best equipped for wide area network interfaces.
They sit at the edge of the enterprise and in the core backbone, right?
Exactly. Communicating with other routers to determine the most efficient paths for data to travel across vast geographical distances.
Then you have specialized connectivity devices like media converters.
Right, because in a large enterprise, the physical network isn't always homogeneous.
No, you might have fiber optic cables running vertically through the elevator shafts to handle massive backbone traffic, but you have traditional copper Ethernet cables running horizontally across the ceiling to connect to the actual desks.
And they speak different physical languages. A media converter is a physical layer 1 device that translates the signal from light pulses traversing the fiber into electrical signals traversing the copper wire.
And of course, wireless range extenders and access points,
which take those wired electrical signals and convert them into radio frequencies, regenerating and amplifying signals to ensure mobile endpoints maintain coverage as employees walk through the building.
But as an enterprise scales from hundreds of employees to thousands or tens of thousands, those basic switches and routers hit a processing ceiling, don't they?
They do. They just can't keep up. The architecture has to evolve into advanced switching.
And our sources highlight a critical strategic distinction here. The difference between standard Layer 3 switches and multi-layer switches.
This is a huge distinction.
Now, I look at the pricing catalogs for enterprise hardware. A top-of-the-line multi-layer switch is exponentially more expensive than a traditional high-end router.
Oh, vastly more expensive.
So my catchphrase time. So what does this all mean? Why is an enterprise making that massive investment? What is fundamentally different about the architecture?
It comes down to processing speed and the depth of packet inspection at critical, high-volume choke points.
Okay, unpack that for me.
A traditional Layer 3 router looks at the IP address, which lives at the network layer of the OSI model to make its routing decisions. It reads the destination IP, consults its routing table, and forwards the packet out the correct interface.
So it's basically just looking at the address on the outside of an envelope to decide which sorting bin it goes into.
Exactly. But a multi-layer switch is an entirely different beast.
How so?
It possesses specialized silicon application-specific integrated circuits, or ASICs, to inspect packets much, much deeper, operating all the way up at the application layer, layer 7.
Huh. So, sticking with our analogy, if a layer 3 router is just looking at the outside of the envelope, a layer 7 multi-layer switch is actually ripping the envelope open, rapidly reading the letter inside, and making a forwarding decision based on the specific application data.
That is an excellent analogy. A multi-layer switch can recognize this packet isn't just heading to IP address 10.1.1.5. This packet contains a highly specific SQL database query, so I'm going to prioritize it and forward it over this dedicated high-speed link.
That's incredibly intelligent.
It is, and these multi-layer switches are deployed deep in data centers and server farms where you have these many-to-one network choke points.
Like when 10,000 employees all try to access the same centralized payroll application at 9:00 a.m. on Friday.
Exactly. A standard router would completely bottleneck under that load. A multi-layer switch processes those requests at true wire speed.
And to complement this, enterprise architects utilize what's known as distributed switching architecture, right?
Yes. Instead of funneling every single piece of traffic from the edge all the way up to one massive central core switch for processing.
Which creates a huge traffic jam.
Right. They push high-speed processing power closer to the user. They deploy 10 gigabit or even 40 gigabit Ethernet switches down into the distribution and edge layers.
So you are distributing the computational load. By processing traffic closer to the source, you massively reduce latency and enhance overall network resilience.
Absolutely. But raw performance is only half the battle. You also have to secure that massive volume of traffic.
And the hardware for enterprise security is highly specialized. Let's run through some of them. We have IDS and IPS intrusion detection systems and intrusion prevention systems.
These are dedicated appliances that sit at the network perimeter, right where the internet enters and exits the building.
Performing deep packet inspection to identify malware signatures or abnormal traffic patterns.
Right. We also utilize VPN concentrators, which are robust hardware appliances designed solely with the cryptographic processing power required to terminate hundreds or even thousands of secure encrypted remote connections simultaneously.
Because regular routers would choke on that encryption load.
Exactly. Then there are proxy servers, which act as middlemen for outbound internet traffic.
So if an employee requests a web page, the request goes to the proxy, and the proxy fetches the page on their behalf.
Yes, which masks internal IP addresses from the outside world and allows for aggressive content filtering.
And crucially, load balancers. These are appliances that sit in front of server farms. As thousands of web requests flood in, the load balancer intelligently distributes that traffic across a cluster of multiple servers.
Ensuring no single server gets overwhelmed and crashes.
Right. Which brings us to a highly debated piece of security hardware, the UTM.
The Universal Threat Management Device.
Yeah. A UTM is essentially an all-in-one Swiss Army knife. It's a single physical box that contains a firewall, anti-malware scanning, spam protection, intrusion detection, and VPN capabilities.
Everything in one box.
Right. On paper, that sounds absolutely incredible. If one box can do everything, why wouldn't a Fortune 500 company just buy a massive UTM and simplify their entire security architecture?
Because of the harsh realities of processing overhead and throughput limitations.
The bottleneck.
A huge one. A UTM is a fantastic, highly efficient, simple-to-install appliance for a small to medium business with maybe 100 employees.
Sure.
But when you force one single piece of silicon to unpack every single packet, inspect it for malware signatures, cross-reference complex firewall rules, filter for spam, and encrypt VPN tunnels simultaneously,
It creates a catastrophic bottleneck. Let's illustrate this with a story to really hammer the point home. Imagine a massive commercial retail enterprise. We are talking about a major big box retailer.
Okay, I can picture it.
On a normal Tuesday in April, their e-commerce site might see 100,000 unique visitors. But on Black Friday, they see 5 million visitors, generating gigabits of traffic per second.
Massive spike.
If their IT architects had routed all that Black Friday traffic through a single UTM appliance.
Oh man, the CPU on that box would hit 100% utilization in 3 seconds.
And the hardware would essentially melt down. The e-commerce site would crash instantly, costing millions in lost revenue.
Which is exactly why large enterprises utilize discrete, specialized hardware instead of UTMs.
Let's trace that Black Friday traffic through enterprise architecture. As that massive wave of web traffic hits the network perimeter, the very first thing it encounters isn't a firewall, is it?
No, it's a dedicated discrete IPS appliance. That appliance has one job, rapidly scrubbing the incoming traffic for volumetric DDoS attacks and known malware signatures.
And once the traffic is scrubbed and deemed safe, it hits the load balancers.
Right. The load balancers look at the massive server farm, maybe 100 identical web servers, and they distribute the incoming HTTP requests evenly.
Ensuring no single web server spikes past 70% capacity.
Exactly. And sitting behind those web servers, acting as the interface to the backend databases, are the multi-layer switches.
Doing the heavy lifting.
Yes, instantly routing those complex database queries at layer 7 speeds to ensure that customers' shopping carts update in real time without latency.
So the entire infrastructure is segmented, specialized, and distributed. No single device is doing all the work, which completely eliminates single points of failure.
It really is a beautiful, highly orchestrated machine.
But I have to bring us back down to reality here.
Uh-oh.
All of this architectural brilliance, the MPLS clouds, the multi-layer switches, the load balancers, it is entirely 100% useless if you don't know what is actually connected to it.
Ah, yes.
Which transitions us into what is arguably the most difficult challenge in modern IT management: asset visibility.
Is the hardest part of the job.
There is an old, unwavering cybersecurity adage: you cannot secure what you cannot see.
Visibility is the absolute bedrock of network security. If you don't know a device exists on your network, you can't patch it, you can't monitor it, and you can't protect it.
So asset visibility is generally broken down into 4 main domains, right?
Right. Hardware asset management, or HWAM. Software asset management, SWAM. Configuration settings management, CSM. And vulnerability management, VUL.
Now, our sources note a very interesting technical reality here. Hardware assets are generally much easier to discover and track than software assets. Why is that?
That's because hardware tracking is network-based. A physical laptop, a printer, or a router has a MAC address and an IP address. It has to broadcast its presence on the wire to communicate.
So network scanners can just ping those addresses and map the physical devices easily?
Exactly. Software, however, requires host-based interrogation. To know what exact version of Adobe Acrobat is installed on a laptop, you can't just scan the network.
You actually need an agent installed on the endpoint's operating system to report back the registry files and software directories.
Right. It is vastly more complex.
To address this overwhelming complexity, the U.S. Department of Homeland Security established a framework known as the Continuous Diagnostics Mitigation Standard, or the CDM standard.
The CDM standard defines a rigorous, highly structured approach for continuously identifying and prioritizing cybersecurity risks.
And it is no coincidence that the very first foundational capability defined in the CDM framework is maintaining a 100% accurate, continuously updated IT asset inventory.
It all starts with the inventory.
And when we talk about enterprise inventories, we really have to distinguish between the 2 primary types of databases: the AMDB and the CMDB.
Oh, yes. These acronyms get thrown around boardrooms constantly, often interchangeably.
Which is a huge mistake.
There are very different tools. An AMDB is an asset management database. It is the macro-level ledger. It tracks 100% of all assets an organization owns.
This includes IT hardware, but it also includes things that don't plug into a wall or have an IP address, right?
Exactly. Software licenses, insurance policies, intellectual property, physical desks, company vehicles. It is primarily a financial and accounting tool.
A CMDB, on the other hand, is the configuration management database. It is a highly specific operational subset of the AMDB.
The CMDB doesn't care about the company cars. It tracks the granular technical details of the IT infrastructure.
Like the exact hardware specifications of the servers, the firmware versions on the switches, the specific patch levels of the applications.
And most importantly, the complex dependencies between all these systems.
And here is the critical structural dependency. You must have an accurate AMDB as a prerequisite. You can't configure an asset in the CMDB if finance doesn't even know it was purchased and logged in the AMDB.
Very true. Now, true visibility means seeing all powered-on IT assets connected to the network in real time. To achieve this, network administrators rely on lower-level protocols.
Like ARP.
Yes. They use tools like the Address Resolution Protocol, or ARP, which maps an IP address to a physical EMEA address on a switch port. They also use the Internet Control Message Protocol, ICMP.
Which is the underlying protocol behind a standard ping command.
Exactly. They use it to locate and verify that assets are actually alive on the wire.
Okay, I have to stop you here. I really need to challenge this idealized vision of asset visibility.
Okay, let's hear it.
Because there is a glaring, Massive contradiction between the textbook theory we're discussing and the messy reality of corporate IT.
Fair enough.
I have seen organizations spend literally millions of dollars deploying massive enterprise-grade CMDB platforms from top-tier vendors. Yet 12 months later, those same organizations routinely, spectacularly fail their compliance audits.
I've seen it too.
Why? Because a marketing VP decided IT was moving too slow, pulled out a corporate credit card, and spun up a shadow IT cloud server to host a new campaign.
Happens all the time.
And that server doesn't magically appear in the CMDB. You cannot patch a system you don't know exists.
So how does an IT leader ensure their multi-million-dollar CMDB doesn't just become a static, glorified spreadsheet that is hopelessly out of date 24 hours after its launch?
That is the multi-million-dollar question in IT service management. And the answer is that manual polling and static data entry are completely dead.
Dead. If your IT team is relying on periodic, quarterly audits like walking around with a barcode scanner or sending out emails asking department heads what software they bought, your CMDB is already obsolete.
So what's the solution?
The only solution, and this aligns directly with the DHS CDM standard, is continuous automated monitoring.
The CMDB has to be alive.
Exactly. Your visibility tools must be deeply programmatically integrated with your network hardware. When a new MC address appears on a distribution switch port, or when a new virtual machine is spun up in the AWS cloud environment,
The network infrastructure itself must automatically detect the change.
profile the device and dynamically update the CMDB in real time via API integrations. You simply cannot manage compliance or block rogue assets without an automated real-time inventory.
So if you're a manager, your actual takeaway here is blunt. Static spreadsheets are a massive legal liability. Your network must map itself.
Completely agree.
But knowing what is on your network is only half the equation. Once you have that total real-time visibility, you have to enforce the rules. You must tightly, ruthlessly control exactly who and what is allowed to access those assets.
Which brings us to the final and perhaps most critical layer of our infrastructure strategy, network access control.
I like to call this the enterprise bouncer.
Network access control, or NAC, it is the velvet rope, the bouncer, and the VIP guest list all rolled into one highly automated system.
And to understand how NAC makes decisions, we have to look at its underlying foundation, the AAA framework.
The AAA framework: identification, authentication, authorization, and accounting.
Let's break down the mechanics of each phase because the distinction really matters. Phase 1 is identification. This is simply the user claiming an identity, like here's my username, I am John Doe.
Phase 2 is authentication. This is the system verifying that the user is actually who they claim to be. You claim to be John Doe, prove it. Here is my complex password, and here is the biometric push notification I just approved on my registered smartphone.
Once authenticated, we move to phase 3, authorization. Just because you proved who you are doesn't mean you get the keys to the kingdom.
Exactly. Authorization is the process of consulting predefined policies to see what specific resources that verified user is allowed to access.
You are John Doe, and we verified your identity. However, your role is in human resources. Therefore, you are authorized to access the payroll server, but you are explicitly denied access to the engineering department source code repository.
And finally, phase 4 is accounting. This is the meticulous capturing of audit trails. We recorded in the centralized log server that John Doe accessed the payroll server at 2:15 p.m. and downloaded a 5-megabyte file.
To execute this AAA framework across thousands of logins a second, enterprises rely on underlying cryptographic technologies integrated into an identity and access management, or IAM, system.
You will frequently encounter protocols like Radius Remote Authentication, Dial-in User Service, and TCAS plus LAG.
These are the protocols that your network switches and VPN concentrators use to communicate securely with a central authentication server.
And our sources also highlight Kerberos, which operates quite differently and is structurally fascinating.
Kerberos works via a ticketing system to permit endpoints to communicate securely over non-secure networks. The mechanics of Kerberos are brilliant. Instead of setting your password across the network every time you want to open a file, which could be intercepted by a packet sniffer, you authenticate once with a central key distribution center.
Right, and if your credentials are valid, the server issues you a ticket granting ticket, or a TGT.
I always explain this like a wristband at a massive theme park. You show your ID and pay your money at the front gate once. They put a secure, tamper-proof wristband on you.
And from that point on, you don't need to show your ID at every single roller coaster. You just flash the wristband.
Exactly. In Kerberos, the endpoint just presents the cryptographic ticket to the application servers. The password never traverses the wire again, rendering packet-sniffing attacks totally useless.
It is a phenomenal implementation of symmetric cryptography. Now, IAM systems and protocols like Kerberos handle the user side of the equation. They verify the human.
But Network Access Control NAC handles the device side. NAC provides uniform, centralized access control across both the wired Ethernet ports and the wireless networks, heavily relying on the IEEE 802.1x standard.
So NAC doesn't just ask, who are you? It asks, what specific piece of hardware are you using? And is that hardware safe enough to touch my network?
Exactly. NAC pre-authorizes devices down to the endpoint level. And to achieve the granular visibility required to enforce these controls, modern NAC solutions utilize 3 distinct methods of discovery.
First, active polling. This is where the central NAC server constantly aggressively queries the network infrastructure, the switches, the routers, the VPN concentrators, asking for a real-time list of every MAIC address currently connected to their ports.
Second is live scanning. This is where the NAC system directly probes the endpoints themselves. It uses ARP requests, ICMP pings, MF port scans, and SNMP queries to aggressively interrogate the devices and figure out what operating system they are running.
And third is passive monitoring. This is much more stealthy. The NAC appliance sits quietly on a span port, capturing and examining the IP protocol interactions and dialogues as traffic flows by.
By analyzing the behavior of the traffic, the NAC can accurately profile the device without ever directly interacting with it.
And here's where the concept of NAC becomes incredibly powerful. NAC doesn't just identify a device, it forces the device to undergo a rigorous posture compliance check before it is ever allowed to access the corporate network.
This is the holy grail of active network defense. Let's walk through the mechanics of that. An employee walks into the office after a 2-week vacation and plugs their laptop into a wall port.
Instantly, the NAC system intercepts the connection. Using an installed agent, the NAC profiles the laptop, it checks the operating system version, it checks the exact patch level.
Is the antivirus running, and are the definition files updated to today's date?
Are there any unauthorized peer-to-peer applications installed? Is the host-based firewall enabled?
If the laptop passes all those checks, it is seamlessly granted access to the production VLAN, and the employee starts working.
But if it fails, if the NAC realizes this laptop missed a critical 0-day Microsoft security patch released 3 days ago, the automated NAC policies instantly kick in.
It doesn't allow the laptop onto the network.
No. Instead, it dynamically reconfigures the switch port to restrict, block, or quarantine the device. It drops the laptop into a heavily restricted remediation VLAN, where the only thing the laptop can access is the internal patch server to download the required updates.
NAC is the ultimate bridge between asset visibility and perimeter security. It takes passive observation and transforms it into active, automated, ruthless defense.
Absolutely.
Which brings us full circle. I want to return to the opening hook I presented at the very beginning of this deep dive.
The thermostat.
The thermostat. The catastrophic Monday morning breach that brought a Fortune 500 company to its knees, all caused by a single, unpatched IoT smart thermostat plugged into a forgotten Ethernet port in a remote edge warehouse. If that enterprise's executive team had implemented the physical infrastructure strategies and the strict access controls we discussed today, how would that Monday morning have played out differently?
It wouldn't have been a catastrophic breach. It would have been an entirely invisible non-event.
Walk me through it.
Well, the exact millisecond a maintenance worker plugged that thermostat into the Ethernet port on the edge switch, a properly configured NAC solution would have detected the link state change on the port.
Using passive monitoring and active endpoint profiling.
Right. The NAC system would have immediately identified that the device's MAC address belonged to a consumer IoT vendor, not an authorized corporate laptop.
It would recognize that the thermostat didn't possess the required 802.1x cryptographic certificate. It couldn't authenticate against the Radius server.
And it completely failed the security posture requirements because it couldn't run a corporate antivirus agent.
Precisely. The NAC policy engine would have evaluated those failures in a fraction of a second.
It would have instantly quarantined that rogue ML address, dynamically assigning that specific switch port to a completely isolated dead VLAN.
That VLAN would have absolutely no routing access to the core backbone, no access to the distribution network, and no path to the data center.
Furthermore, the NAC system would have automatically generated a low-level alert to the Network Operations Center, logging the exact geographic location, the specific switch host name, the port number, and the time of the event.
The crisis is completely averted, handled by automated silicon before a single malicious packet can traverse the corporate interstate.
And that reality defines the paramount actionable takeaway for this entire deep dive. You must implement identity and access management with multi-factor authentication deployed seamlessly alongside a robust, continuously monitoring NAC solution.
This is the only technological way to ensure true zero-trust principles for all your mobile, remote, and local workforce connections.
The physical infrastructure is the road system. The foundational network services are the traffic laws. And network access control is the ruthless law enforcement. You need all three functioning in absolute harmony to secure an enterprise.
Which brings us to our strategic closing. As a corporate manager, an IT director, or an operations executive, your primary takeaway today is this: a well-architected physical infrastructure understanding the vital differences between your edge, your distribution, and your highly critical core networks, paired with strict IPAM methodologies and continuous NAC visibility, is the only way to safeguard a modern enterprise.
It is how you transform a catastrophic IoT vulnerability into a routine, automated quarantine log entry that nobody even stresses over.
It is about fundamentally shifting your organization from a reactive posture, waiting for the firewall alarms to go off, to a proactive, automated structural defense.
But as we master and secure this massive wired infrastructure, we have to prepare to cut the cord entirely.
Yes, managers, you must stay tuned for our next installment, Chapter 10, Wireless Networks. Next time, we are going to solve the next massive technical puzzle,
Exploring how the IE 802.11 standard family, advanced MU-MIMO architectures, and precise radio frequency wireless site surveys drive corporate mobility and empower frontline workforce productivity.
It is a completely different ballgame when your proprietary corporate data isn't locked in a copper cable, but is literally flying through the air in the break room.
The transition from wired networks to widespread corporate wireless brings incredible operational flexibility, but it introduces an entirely new, incredibly complex set of physical and logical security challenges that executives must understand to prevent interception.
Absolutely. It's going to be a crucial discussion. Once again, I want to invite you to like, subscribe, and share this deep dive. Please check out the description below for links to the architectural diagrams, the corporate resources, and the technical readings that support Chapter 9.
And while you're exploring the channel, I highly encourage you to review our other corporate IT playlists and video modules designed specifically for continuous professional education.
If you found today's deep dive into network security architecture valuable, you will definitely want to check out our other dedicated podcast series hosted on the channel, Digital Forensics and Network and System Security.
And we look forward to having you back for Chapter 10, Wireless Networks.
But before we go, I want to leave you with a final, slightly provocative thought to mull over.
Go for it.
Throughout this entire deep dive, we have emphasized the absolute non-negotiable necessity of automated continuous diagnostics mitigation, the CDM standard and centralized databases like CMDBs to track, pull, and secure every single asset on your network. We want total visibility. We want a central dashboard that sees everything.
Right, the panopticon.
But as modern enterprises rely so heavily on these omnipotent centralized management systems, what happens when the monitoring software itself becomes the target of a sophisticated supply chain attack?
Oh, wow.
If the very system designed to see everything and enforce the rules is compromised from the inside, quietly distributing malicious updates to all your highly trusted endpoints, who is monitoring the monitors?
It's a chilling architectural paradox, and one that requires a complete rethinking of zero trust at the software layer.
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.